The Big Bang is the scientific story of creation. The entire universe, all space-time, emerged in an instant 13.7 billion years ago. It's an extraordinary idea. It's audacious. And so, of course, scientists shouldn't believe it unless there's good evidence to support the theory. In fact, there is very good evidence. The Big Bang is accepted by essentially all cosmologists. The primary pieces of evidence for an early hot dense phase of the universe are the expansion of the universe itself, discovered by Hubble. Tracing this backward leads to a prediction of a time when all galaxies were on top of each other. The microwave background radiation itself, which fits perfectly with the idea of an early hot dense phase, and the correct abundance of the light elements, which occurred when the universe itself was the temperature at the core of a star, a few minutes after the Big Bang. This model, so far, agrees with all current observations. So it's supported by a web of evidence and not just any one single piece. Also, there's a lot of indirect evidence from galaxies and the way they're distributed and the way they behave that the universe was smaller and hotter in the past. Since general relativity, the theory that describes expanding spacetime, is based on the concept of curved spacetime, one of the most important things we can measure about the universe is its space curvature. This was very difficult to do until the microwave satellites were launched. But with WMAP, a beautiful measurement of space curvature was produced. The concept is quite simple, and it's based on the fact that there's a characteristic size to the speckling pattern you see in the temperature map of the microwaves, of about 1 degree. If you think about it, these microwaves have traveled freely through space across 40 or so billion light years and for 13 billion years of time. If space were curved, the speckle pattern at the time of release would suffer magnification or demagnification depending on the nature of space curvature. If space were positively curved, the characteristic speckle size of 1 degree would be magnified by intervening curvature. If space were negatively curved, that characteristic angular scale would be demagnified, and if space were flat, it would stay the same. The microwave satellite therefore allows us to test by looking at the angular scale and comparing with a theory whether space is curved. The result is emphatic and simple. Space is not curved. Space is flat to within a couple of %, and this becomes one of the constraints on the Big Bang model, and a clue to the behavior of the universe. The Big Bang model is extraordinarily successful, but nearly from its inception, it was realized that there were several problems with it, or aspects of the universe not well explained by the model. One of these became known as the flatness problem. As described, space turns out to be very close to flat. Another aspect of this is the fact that the matter density of the universe, mostly composed of dark matter, is within a factor of a couple of the matter density needed to overcome the cosmic expansion and cause the universe to recollapse. A factor of 2 or 3 may sound like quite a large factor, but if we trace the expansion backwards, this actually implies extraordinary fine-tuning in the very early universe. Apparently, in terms of the initial conditions, the universe was poised close to a knife edge between eternal expansion and subsequent recollapse. The Big Bang provides no explanation for this, for why the universe is so close to being spatially flat. To think about this a different way, imagine hypothetical universes. Suppose the universe had different initial conditions. If the matter density had been a little bit higher, the universe would actually have recollapsed, perhaps long ago, perhaps after only a few million years of evolution. That's an unrecognizably different outcome. If the matter density had been much lower, the universe would have expanded at a more rapid rate, and in fact under many scenarios would have expanded so rapidly that galaxies and stars would not have formed at all. Remember, the structure formation we see takes place competing against expanding space-time. This fine-tuning has no simple explanation in the Big Bang model. To understand other issues with the Big Bang, we have to introduce the idea of horizons. We're familiar with the type of horizon we have on the Earth. On the curved surface of our planet, there's a limit to how far we can see in any direction because of the curvature of our planet. This is a familiar type of horizon. Black holes give us another concept called the event horizon, which is a boundary in space and time beyond which we cannot see. Information is trapped within an event horizon. In cosmology, there's a third form of horizon that comes into play, and it's called a cosmological horizon. It's essentially an information boundary because photons, or information, has not had time to reach us in the history of the universe, 13.7 billion years. To see why this is an issue, let's consider the expansion of the universe. In terrestrial laboratories, light travels simply from A to B. We can coordinate observations, synchronize clocks, and make measurements that always recover the speed of light as a constant number, 300,000 kilometers per second. The early expansion of the universe in the Big Bang model was actually faster than the speed of light. It's a simple consequence of applying the theory of general relativity to the expanding universe. You might think, didn't Einstein say that the speed of light was an absolute limit? He did, but that was his special theory of relativity, which applies to what are called inertial frames, situations like the laboratory or within the solar system, where we can synchronize clocks and where signals move simply from one place to another. The cosmic situation is quite different because of expanding space-time, and the situation is governed by general relativity, not special relativity. Einstein's general theory applies no speed limit to the universe. If it wants to, it can expand faster than light, and it turns out for most of the history of the expansion, any 2 points in space were actually moving apart at the time the light was emitted faster than light speed. This creates the extraordinary situation that when we look at the light from distant galaxies, and these are not particularly distant galaxies, Hubble Space Telescope and other large telescopes measure thousands of them. When we look at the light from these galaxies, we're looking at light that when it left the galaxy, the object was moving away from us faster than light speed. The only reason we see the signal is because since that time, the universe slowed down its expansion rate and that light was gradually able to reach us. The implication of superluminal or faster than light expansion of the universe is that there are regions of space we've never seen, and indeed many that we may never see. Put simply, the physical universe, all there is larger than the observable universe, what we can see with our telescopes. How much larger? The theory doesn't actually say. It may be vastly larger. One important attribute of the microwave background that's been known since its discovery is its incredible smoothness, or isotropy. The fact that the intensity, or the temperature, which is what's actually measured, is essentially the same in every direction of the sky, to better than 1 part in 1,000. If we could imagine the microwave background as a pond 100 meters across, the largest variations up or down in intensity are just a few millimeters. It's almost perfectly smooth. Why should this be a problem in cosmology? It became what's known as the smoothness problem. The reason it's a problem is part of the Big Bang model. If we go back to the time this radiation was produced, 400,000 years after the Big Bang, the universe was in an early and extremely rapid phase of expansion. The expansion rate of any 2 points in space were over 50 times the velocity of light at that early time, and have subsequently slowed down enormously. We can see why this is an issue by thinking about how energy travels in the familiar universe. If energy travels in your house or in your kitchen by radiation or conduction, it must travel from a hotter to a cooler place, and gradually the temperature is equalized. This is what happens when an ice cube melts. When we touch a hotter surface, the heat travels through our fingers and reaches a lower temperature. Basically, any two objects that are in thermal equilibrium reach the same temperature. If they are out of equilibrium, they can have different temperatures. Reversing that logic, when we see two regions of space or two objects that have almost exactly the same temperature, they must be in thermal communication or thermal contact. And the fastest that information can travel is the speed of light, by radiation. But what we see in the microwave background is that any two patches on the sky, either adjacent or on opposite sides of the sky, have almost exactly the same temperature or intensity. There's no way this could have happened because in the very early universe, those regions were moving away from each other far faster than the speed of light, and so could not have reached thermal equilibrium. In other words, the smoothness or isotropy of the microwave background has no explanation in the standard Big Bang theory. To the smoothness and flatness problems was added a third, called the relic problem. This is a little more esoteric and depends on high-energy physics. But in the infant universe, various defects in space-time, so-called topological defects like strings, should have been quite abundant, and we should expect to see some relic of those left over in the universe. But no one has ever detected experimentally a rupture in space-time or a fissure or a cosmic string, and so their lack of abundance has no easy explanation in the Big Bang. It's not just that space is smooth and flat, it's also incredibly clean. These were three issues that weighed on people's minds in the 60s and 70s as the Big Bang model took hold. In the early 1980s, a physicist called Alan Guth, working at MIT, developed a new wrinkle on the Big Bang model called the inflationary hypothesis. This speculative idea involves the universe going through a rapid exponential expansion extremely early in its history, roughly 10 to the minus 35 seconds after the Big Bang. This, hypothetically, was a time when all the forces of nature except gravity were unified in a grand supersymmetric theory. Plausible mechanisms were deduced by high-energy physicists whereby energy from the unification of the forces and their subsequent separation could be used to drive exponential expansion of space-time. Essentially, in this tiny fraction of a second after the Big Bang, the universe expanded from smaller than the size of a proton to about the size of a basketball. It then continued its subsequent, more sedate expansion, the one that leads to the Hubble expansion we observe today. Inflation automatically solves the flatness and the smoothness problem. Regardless of the initial highly curved space-time, when the universe was the size of a subatomic particle, its inflation by orders of magnitude in a tiny fraction of a second would have smoothed out space-time to be essentially flat to our view. The smoothness and flatness go together, but of course they were the motivation for inflation in the first place. Inflation would have also thinned out the presence of cosmological relics, space-time relics like strings and monopoles, to the point where we shouldn't expect to observe them in the nearby universe, explaining their absence from experimental data. Inflation has an enormous implication of vast amounts of space-time beyond our view, because they were carried far from our view ever through telescopes by this early exponential expansion. Inflation essentially says that the physical universe is enormously, orders of magnitude larger than the observable universe we see with our telescopes. It's an extraordinary hypothesis, and it's posited in physics of the very early universe. In microphysics we don't yet understand. There is as yet no single or unique grand unified theory that unifies the forces of nature, except gravity, in a way that can be experimentally verified. So as such, inflation is a speculative hypothesis, but it does account for some basic features of the observable universe. Cosmologists have used exquisitely detailed observations of the microwave background enabled by satellites like WMAP to test inflation for the first time in the last few years. One of the generic predictions of inflationary models is that the power on different scales in the microwave background should vary very slightly from being equal on all scales. Generally, the simplest form of power law variation is equal power on all scales. But inflation predicts what's called a slight tilt in the power spectrum. That tilt, shown as the index in a power law of the amount of power on different angular scales, is actually observed. So microwaves provide one early indication that inflation is an accurate theory, that the universe may well have gone through this extraordinary phase very early on. Future tests of inflation are going to be harder yet. A microwave satellite called Planck, which has started its work a year or so ago, will be able to test inflation too, as will polarization measurements of the microwaves, which requires extraordinary precision. But perhaps the ultimate test of inflation involves the detection of gravity waves from the infant universe, for which we'll have to wait for LIGO. To summarize the status of the Big Bang model, it's in robust health. Astronomers have no other explanation for the microwaves we see all around us, and it also accounts for the observations of galaxies through large telescopes. The Big Bang theory has been embellished to include an inflationary era as a means of explaining why the universe is so flat and so smooth on very large scales. The Big Bang model is a physical explanation of all that's happened to space and time in the last 13.7 billion years. It does not propose a cause. The Big Bang model never says why the universe exists in the first place. That's in the realm of philosophy or metaphysics. The basic Big Bang model has experimental verification from the abundance of the light elements, galaxy redshifts, and the microwave radiation. But it doesn't on its own explain the smoothness or flatness of the universe. The inflationary model was produced in the early 1980s to explain those events in terms of an early exponential expansion of the universe caused by unification of 3 out of the 4 forces of nature, all the forces except gravity. Inflation has begun to get the first hints of experimental verification in terms of detailed microwave observations. An exciting frontier in cosmology will involve confirmation of the fact that inflation actually occurred.